Now let's focus on the module costing techniques. So as a reminder, everything here is in terms of what does the costing or the limits or the boundaries of our estimate will be, okay? So remember, chemical plants can be part of an integrated complex. That means that you're just adding to an existing plant that has the ancillary facilities to support the personnel and the process, right, that you're designing. Or you can have a grassroots plan basically that is a brand new space. So the plan addition or the process that you're designing are the units, these blocks that you see in the middle, that is called the process, unit operations, and they are contained within the battery limits. The bare module cost is the cost to purchase and install the unit, let's say this circle, right, that you have here, this unit, and this unit. So each equipment in the process, you will be calculating the bare module cost. That bare module cost includes the direct project expenses, the indirect project expenses that I explained before. All of these terms I include them before. Also the freight, insurance, and taxes. So once you do that, you understand and calculate any deviation from base conditions for each equipment. Then you're gonna add it up, and we're gonna multiply by a factor to calculate the total module cost. But notice that the total module cost is within the battery limits. It's just about the process. That includes the factor, like I mentioned, is a factor of the total, the addition of all the bare module costs for each equipment at the right process conditions, and also include contingency fees. If your design is part of an integrated complex, this is where you stop. If your plan is from scratch, it's a completely new plan, then you need to calculate what is called the grassroots cost. That includes, right, a factor that includes the total module cost, right, in auxiliary facilities. So notice all of the auxiliary facilities that are needed in order for you to do the capital investment. I want to point out that the utilities and the waste treatment and the solid disposal, they're part of the costing, but not of the fixed capital investment. Those are things that we pay every year, every month. So they are going to be part of the operational cost of the plant. Think about the battery limit is the house that you're purchasing and all of the equipment like the fridge, your furniture, everything that you need inside. And then the operational cost will be anything that you need to support your house and all of the utilities for your house, including Netflix, your cable, Wi-Fi, whatever you need, right? Water, electricity, and so forth. This is really important because students get confused about about all of this costs. So please make sure that you know the differences between them. These are the equations that we are going to be using. This is based on Turton's book and the bare module cost method that he uses. There's other type of methods and equations that you can use. They're typically modular, and modular, it is a module technique because it considers each equipment as its own module, right? It's like a group of different things that depend on the type of equipment and the cost of the equipment. So that's why it's called a modular technique. We're using this equation because we're going to integrate this calculation with a software that I already have that is called CapCost. So the idea is that we're going to use HYSYS, try to size and get all the information from HYSYS, and then bring to this software the information about the economics. And in that, it's an Excel sheet. Basically, it's not a software. It's just an Excel sheet where all of these calculations will be done for you. Okay, so you're going to be able to do complex analysis of the profitability of a plan just using this spreadsheet that I'm gonna give you. But as a good engineer, I'm gonna teach you how to use it, and you're gonna complete an assignment doing the mathematics behind that spreadsheet before I present it to you, right? I want to make sure that you know how to do the math before we go and use the software. Anyways, these are the equations that we have. Notice that for all of them, basically the most important thing that we have to do is to calculate the purchase cost of the equipment, and from there we can get all of the terms. Okay, so let's start. So the bare module cost, it could be the bare module cost as standard conditions or non-standard conditions. And I know that, or base conditions, I know that the C naught is the bare module cost if the process is being operated as standard base conditions, which is 1 atmosphere and a materials of construction of carbon steel. And then CBM without the naught means that there are deviations in terms of pressure or in terms of materials of construction as compared to the bare module cost at base conditions. So remember, it includes direct, indirect, contingency, and fees are expressed as a function of purchase equipment costs at base conditions, as I mentioned. Each equipment type has different multipliers, right? A heat exchanger, the installation, the contingency, and the fees are different than a compressor, than a vessel, etc., etc. So every equipment will have different multipliers. I'm giving you a PDF with this appendix, which basically has all the equations that Capcost, which is the software that the spreadsheet that we're going to use, actually embeds in it, but you have them available for you to complete any assignment related to this. The bare module cost, right, is defined like this. It has this form, okay? So you have the purchasing cost of the equipment cost, right? This is at base conditions. That's the important thing, right? And then you have FBM, that is called the bare module cost factor, and it's a multiplication factor that account for the items in table 6.7.7. I'm going to show you that table in a second, plus the specific materials of construction and operating pressure. So what we're going to do is trying to get the bare module factor, that is a modifying factor from the base, from the purchasing cost of the equipment. So we know that we can purchase the equipment, go there and purchase an equipment. And I know that a heat exchanger costs different than a vessel, right? So I know that the factor will also be different depending on the type of equipment. If I'm dealing with a heat exchanger, the electronics, the contingency fees are going to be different than I have a high pressurized vessel. Each equipment and each deviation from base conditions will have a different bare module factor. So once again, as a recap, I have mentioned this a lot. Base conditions are when units operated at near ambient pressure, unit fabricated from most common material, and that is carbon steel. Okay, any material that is not carbon steel will be a deviation from base condition. Therefore, it's going to have a penalty in the bare module factor because we need to calculate a material factor. And you're going to see that in the formula of FBM very soon. If you have an equipment that is also operated outside the base conditions, right, in terms of pressure, there's going to be a penalty, cost penalty associated to that, because not only now you need a material, an equipment that has probably a different material construction, but also pressure affects the thickness of that material because it has to contain, right, or hold the pressure inside. The knot is specifying that the calculations and the number that I'm using are under base conditions. However, even if the process is at base conditions, you will have a bare module factor, because the bare module factor, remember, includes direct and indirect cost. So you always gonna have a multiplier. The thing is that if you operate it outside base condition, that multiplier will be higher because you have penalties associated due to changes in pressure and materials of construction. This is the module factor approach. Again, these are the different terms. So the first thing that we have to do is get information on how to get CP, which is the base, the purchase cost at base conditions. So we already went through this in previous videos, right? You can use data from similar equipment for other years. That means that if you do that, you have to make sure that you adjust this in terms of the year, that, right, the effect of time, and also the effect of capacity. So you may need to use the cost index and the 6/10 rule, or if you know the exponent, right, you can calculate the relationship between cost and changes in capacity. So it is reasonable, accurate, right, to calculate this using this information. You can also use cost estimating charts and scales for time. That's perfectly fine. An example is the one that I'm showing you here. So those cost estimating charts and scales for time also uses can be converted into equations, right? So if you have a lot of information from multiple equipments, you can just condense that into a graphic form, and from the graphic form then you can linearize, right, and get an equation that looks like this. This type of equation, right, if you don't have any other type of information, like I mentioned before here, prices from other equipment or prices for similar equipment at different time. So this is the most the best way to go because it's just simpler. But if you are lacking all of that, then what you can do is use these equations to calculate the CP. Notice that this equation is to calculate the purchase cost of an equipment based on the attribute. This is A is not area necessarily, is attribute. So each equipment will have a different attribute. Once again, using the data for the purchase cost of equipment at ambient operating pressure and using carbon steel construction, we can feed all of this information into an equation. And the good thing that I have is that the sources for this lesson, the book is all about that. This person used a lot of data from 2011, and this group of authors actually condensed all of that data into this equation. And this is a very important resource for any engineers. You can also use the Paris, or you can use the book that we're currently using right now. And you can see that they also have their own way to do the module factors. Okay, so important things to remember. A is not necessarily the area. This is the attribute, okay, or the capacity or size parameter for that particular equipment. The values of K, the K values that you see here, the constants, they apply within a range of values, right? Minima with a maximum and a minimum. So anything besides that, you're extrapolating. So that's why you see, you have to be very careful with a large extrapolation, okay? But they're useful, right? Because the data is available and helps to do preliminary estimates. So what I'm gonna do now is show you these tables. Once again, in the module, you should be able to download these tables, and I recommend you to stop now and maybe have them so you can identify them and see in what equation you should be using that table. That's my recommendation for you to be able to complete any assignment related to this. So this is table 1, A1. So table A1, notice it has the K values on the top and it goes with the CPs. Okay, so it's the only equation that has K values or K constants. So to calculate the purchase cost at base conditions, basically you're gonna go here. So let's say that we're doing a compressor that is rotary. Notice that the attribute between compressors, here you have fluid power, kilowatts, is different than conveyors that uses areas. So here, this is A is the attribute. The A that you see here in this equation is basically what type of attribute. From HYSYS, this is what you get. This is exactly what you get from HYSYS. You're trying to design an equipment, and from that equipment, you're getting the capacity and then convert that into cost, okay? So notice here that you have the K values that you can use, and that it tells you the minimum and maximum size for these values to apply. So here is 18 kilowatts to 950 kilowatts, right, of fluid power for the rotary compressors. Notice that every equipment is different, has different values, and has different effects on the cost. Once again, these are all the equipment: heat exchangers, heaters, mixer. You have reactors, screens, towers. This looks horrible, but in your you should have it okay on your PDF. You can also use, similarly to have equations, right? You can also use graphs. And when you use graph like this, right, you have here the capacity. And from the capacity, then you can measure the unit of, the cost per unit of, per unit, right? If you're talking about shaft power, whatever it is. So here you can get also a conversion factor to calculate the purchasing cost for that equipment based on the area that you're looking for. Notice that here, for example, these tables, they're all stamped for the year 2001. So anything that you do with this table, they have to be converted to 2019 or 2020, whatever is the year, 2021, whatever is the year you're living right now. So notice that this equation is stamped with time. So make sure that you are aware of that when you're using this equation or any data in terms of cost. So the next thing, right, once you decide the purchase cost, remember you have to make sure that that purchase cost is already converted to the right capacity and is also corrected by the time, right? The time you're doing the economic analysis for. So I recommend you to do that, because if you don't do that now, then you have to remember to do it at the end when you calculate the module cost. But if you do it now, you know that everything is at the same year and you don't have to deal with that later. So make sure that all of the equipments are already converted here when you calculate the CP, the purchases cost, at the right year where you're going to do the economic analysis. So the next thing that you're going to do, right, is to get the bare module factor. And these are a sum of multipliers. They depend on the type of equipment and unit that you're costing. So we're going to dedicate some time on this now.